All right, welcome to the Nearly Carbon Neutral Geometric Topology Conference. Um, I will be giving two talks. One is an actual research talk about quotients of Coxeter groups. And since I'm not assuming that everyone knows what a Coxeter group is, I am also giving this talk, which is an introduction to Coxeter groups, where we will be discussing the definition, motivation, and all these things. So in case you're very familiar with those, this talk will not contain any new information. And if you haven't seen them or haven't seen them in a long time, then maybe this talk can convince you that they are interesting or remind you of like the basics that will be important for the other talk. But even if you don't want to like listen to me talking about Coxeter groups for 20 minutes, you can still understand the other talk, but there will be a lot of black boxes from Coxeter theory. Okay, so what's the plan? What are we doing here? Well, first we want to define Coxeter groups. Then we want to discuss examples. Then I want to give a quick history lesson, so talk about the main contributors, when were they introduced, and these things, because Coxeter groups actually have a very rich history. And then I want to discuss some properties. Um, Mainly properties that we will be needing in the other talk, but not all of them. And yeah, properties that I personally think are interesting and that I personally like. Okay, so definition. I will be giving a definition via simplicial graphs. There are definitions that use matrices, um, whatever you prefer, but for me, this will always be the graph definition. So let gamma denote a finite simplicial graph. That means we don't have um, loops and double edges. And m from e to the natural numbers bigger than or equal to 3 and infinity in edge labeling. Okay, and then we define the Coxeter group as a group with the following presentation. This will look scary at first, but it really isn't. So we will define the Coxeter group, which we will denote by W gamma via the following presentation. So the generators are all the vertices. And the first relation we impose is that every generator has order 2. And then we say the product V times W should have order 2 if there is no edge between them. It should have order of the edge labeling if, well, there is an edge and this edge labeling is infinity. It's not infinity, sorry. And if this edge label is infinity, then we don't have a relation on the product. And if you think about this, for example, this relation, V times W to the power of 2, with this relation V squared, this means that V and W commute. Okay? So this is rather important for the things we will be discussing later on. Okay, so this presentation, maybe it looks a bit scary at first, but it really isn't that difficult, I think. Okay, so first example. I want to tell you that you have definitely seen Coxeter groups, even though you haven't called them Coxeter groups. So the dihedral groups are the first examples, and if you remember from your group theory courses or whatever, the dihedral groups are the symmetry groups of regular 2n-gons. So I have drawn a more or less regular 6-gon here, and then I've drawn in two axes, S and T, or, well, I want to denote the reflections across these axes by S and T. And if you think about this for a while, then, or not super long, then you will realize that the symmetry group of this 6-gon is generated by S and T. Okay? And maybe if you remember from your group theory courses, then you can write this. I denote this by D3. Some people write this as D2 times 3. This is my notation. Okay. Sorry if that doesn't agree with what you learned, but okay. So if you think about this for a while, you will figure out that this group, the symmetry group of the 6-gon, has this presentation. And this very much agrees with what I've drawn here, right? I mean, S and T obviously have order 2. And if you compose them, then you end up with a rotation with angle 120 degrees. And this is the one-to-one correspondence. And if you look at this presentation, this is obviously a Coxeter presentation. So this corresponds to the Coxeter group W gamma with the following graph gamma. We have two vertices, which I've labeled S and T, and then there's an edge labeled 3 here. And similarly, if you don't have a 6 gon but a 2n gon, then you end up with the dihedral group Dn, and this has essentially the same presentation, but the 3 is replaced by an n, and this edge label is also replaced by an n. And this also works for the infinite dihedral group. Okay, so the next example that you may or may not know are the triangle groups. And these are Coxeter groups where the defining graph is a triangle. So you have 3 vertices and you have relations Q, R, and P. And these groups have very interesting properties, and they have also been studied not from the Coxeter point of view, but from different points of view. Yeah. And for me, the cool thing about these groups is that, well, you have to add up the reciprocals of P, Q, and R. And when they are bigger than 1, smaller than 1, or equal to 1, this corresponds to triangulations of different spaces. So if you're bigger than 1, you obtain a triangulation of the sphere. If you're smaller than 1, you obtain a triangulation of the hyperbolic plane. And if you're equal to 1, you get a nice triangulation of the Euclidean plane. And since this is a great opportunity to include some pictures, here are some triangulations of the respective spaces and the corresponding triangle groups. And if you think about this, or if you're sort of familiar with this, if you, for example, look at this vertex here, where there are 4 triangles glued together, this sort of corresponds to commutation in the triangle group. And here at the top, there are more triangles glued together. This comes from this 4, for example. And similarly, in this picture, you can see the same quote-unquote pattern, and here as well. So this is kind of nice, and it gives you very nice pictures. So you can already see that Coxeter groups, or at least these Coxeter groups that I've given you in these examples, are very, very geometric. So in case you like geometry, which I hope you do, since this is a geometric topology conference, maybe this can motivate you that Coxeter groups are very nice objects to study. Okay, one more example is the following graph. Okay, this time we start with a graph. So we take a graph, just a line with n vertices, and all the edge labels are 3. And this is a common convention when you're studying Coxeter groups, that if a label is equal to 3, you don't write it down, because this label somehow appears very, very often, and you don't want to write down a bunch of 3s because mathematicians are lazy. So just imagine there's a 3 everywhere here. Okay, so what group do you obtain? Well, you need to think about this for a while, but if you think about this for a while, then you will figure out that this corresponds to the symmetric group on n+1 generators. And okay, maybe this comes as a surprise to you. So how does one see this? Well, the symmetric group is, for example, generated by transpositions. So these are permutations that just swap 2 neighboring elements and do nothing on the rest. And these generators obviously have order 2, right? And if I take 2 such generators, if they have disjoint support, then their product has order 2. But if they share one vertex and I compute their product, this gives me a 3 cycle. So this is 2 neighboring ones, order 3. And if I take 2 that are not neighboring each other, there's no edge, so they commute. So this is how you get from sim n+1 to this Coxeter graph. And one final note that is sort of important for later on I phrased this as an example, but it's more of a, I don't know, remark or something. So suppose I'm given a graph gamma which has multiple connected components, gamma 1 till gamma n, right? This can happen. What happens to my Coxeter group? Well, then my Coxeter group is, in a natural way, a direct product of these smaller Coxeter groups. Okay. So, history lesson. Where do Coxeter groups come from? Well, they were first introduced and studied by someone called Coxeter, Harold Scott MacDonald, in 1935. And what was being done back then was groups were really, well, one hot topic was reflection groups, and these are groups that come from geometrically from some reflections across hyperplanes in some spaces. And what Coxeter realized is that these reflection groups they come from a presentation that looks exactly like a Coxeter group. And you can sort of go back and forth between them, and this gives you the right framework to study these groups. I will actually give you more details on how he sort of approached this, given the presentation, in part 4. But what I want you to know is that, okay, this was a geometric problem and then was turned into an algebraic problem and then was turned back into a geometric problem by Coxeter in 1935. And what he did is, well, he characterized the finite and affine Coxeter groups by geometric means. I will define an affine Coxeter group later. Essentially, it's one that acts nicely on Euclidean space. But why is this a big problem? Well, if I'm given a presentation or just a group which comes from certain reflections across some hyperplanes in some space, it's actually really hard to tell whether it's finite or not. And this is sort of the first question you would probably ask if you're given an abstract group. Maybe, okay, is this a finite group? Okay. And then the next, major contribution. There has always been active research about Coxeter groups, but I think the next really, really big, quote unquote, breakthrough or, big player has been Jacques Tits in the 60s and 70s. And what he did, first of all, he used Coxeter groups to define buildings. If you know what that is, great. If you don't know what that is, these are very beautiful geometric spaces that can be used for various things. I think they have been used to study sort of certain Lie groups as well. But these are very, very beautiful geometric spaces with combinatorial properties and everything. So this is very, very, it's very important. And he also studied Coxeter groups from sort of the algebraic perspective. For example, he gives a solution to the word problem. And the word problem in Coxeter groups is especially nice to solve because if you want to reduce a word, what you have to do is, of course, you have to use the relations. But you only have to use relations that do not make this word longer. So sometimes you have to use a relation that doesn't make the word shorter. That happens. But you never have to make this word longer. So it's actually possible, if the word isn't too big, to do this by hand, essentially. And of course, a computer can do this very, very fast. Okay, and in the 80s, 90s, this is when really geometric group theory came about with Gromov and all these things. And there were many authors who contributed towards this. Of course, Coxeter groups are one of the natural candidates for geometric group theory because they come from a geometric idea, right? So, yeah. And one of the main contributions that I want to mention here, because I've done work on that as well, is the cat0 property. For example, all Coxeter groups end up being cat0, which is a notion of non-positively curved group, and this is due to Musong in 88. And even today, there is active research on Coxeter groups by many authors. Different questions can be asked for these groups, and many people work on them. And if you want to learn more, the sort of 3 standard references in my experience are a book by Bourbaki, one by Humphreys, and one by Davis, which I will be showing on the very last slide. Okay, so this is the brief history lesson where, of course, you could probably give, I don't know, at least 5 talks just about the history if you really want to mention all the results. But I think this gives you a rough idea that there's a bunch of research that has been done, but still there's somehow open questions. And, well, much is known, but much is unknown. And, yeah, maybe this motivates you to think about these groups as well. Okay, properties. So, finiteness. I want to talk about finiteness. And what's the main tool to study finiteness? Well, a nice representation. So you're given this group presentation, and somehow the idea is that these groups come from sort of quote-unquote reflections. So what we now want to do is we want to use this representation that this group presentation that we had, and now realize this group as a group of reflections. Well, this will not be like actual orthogonal reflections, but this is sort of a generalization of a reflection that we will end up with. Okay. Yeah. Okay. So this looks scary at first, but we'll go through this very, very slowly. So suppose we're given n vertices, right? N generators. And now we want to define a matrix. So what we do is we have to go through all the cases, right? The first case is that we have an edge between Vi and Vj, and the edge label is not infinity. Then we just say, okay, this is minus cosine of pi divided by the edge label. We say this is 0 if there's no edge. We say it's minus 1 if there's an edge, but the label is infinity, which is intuitively what you would get if you would plug in infinity here, right? Pi divided by infinity is 0, cosine of 0 is 1, minus 1 is minus 1. And, well, if I equals j, then we put 1. So why does this cosine appear? This is sort of the intuitive idea is that you want to regain the angle between the hyperplanes, right? If you remember in this dihedral group example, the generator V1 sort of corresponded to the reflection across a vertical hyperplane, and V2 corresponded to a reflection across such a hyperplane. And now what we want to have as the entry ij is sort of the angle, in a sense, between these hyperplanes. And I'm sorry for getting this email. Okay, so now what we do is we say A is supposed to be this matrix above, and now we define big phi from W gamma to GL of R to the N via the following thing. Well, what is this phi of Vi supposed to do with a vector W? It maps W to minus 2 times Vi A WT Vi. So essentially this A it's a bilinear form in a sense, right? And what I want you to note is if you plug in Vi, then Vi is mapped to negative Vi, if I remember correctly. Yes, exactly. So this is sort of this is where this generalized reflection comes in, right? Okay, and what one can show is that this phi, this big phi, is injective, and therefore all Coxeter groups are linear, which is a nice property to have. And of course, like, this is not obvious, okay? That this big phi is injective and does everything the way it's supposed to do is absolutely not obvious. This requires some work, but I'm just trying to give you an idea of why it's true and why this is sort of, well, nice. Okay, and Coxeter did this, right? He wrote this down, and what he showed is that the Coxeter group W gamma is finite if and only if this matrix A is positive definite. And now this really gives you a tool to check whether a given Coxeter group is finite, right? You just write down your presentation, you write down this matrix, and then you can very easily check whether it's finite or not. And this, of course, Coxeter did this as well. Okay, first an example, sorry. Well, if you have the group sim of 4, right, this is this line graph where now we have 3 vertices, and if you go through this definition, this is how the matrix looks. Okay, it's a nice symmetric matrix. It has ones on the diagonal. The other entries are non-positive. Okay, and this corresponds to a certain representation on R3, which I've visualized on S2, because it's, yeah, okay. Um, because I can't draw nice three-dimensional pictures, so I thought, let's just take the sphere and then think about certain reflections. And what you can again see here in how these triangles meet, this corresponds to the 0 here, which corresponds to commutation, and this corresponds to this minus a half, which corresponds to the order 3 of the neighboring products. Okay, and so what is this classification of finite Coxeter groups? Well, okay, so I can't give you all graphs corresponding to finite Coxeter groups because you can, well, if I have a finite Coxeter group, then any finite direct product will still be finite. But apart from taking products, these are essentially the only ones, the only graphs that can occur for finite Coxeter groups, and this is the complete list. So if I have a finite Coxeter group, then it is a product of Coxeter groups whose defining graph looks like this. And these are all. And this can be done using this representation and the fact that positive definite is the same as finite. Okay, now affine Coxeter groups. A Coxeter group W gamma is called affine if it is infinite and it contains a normal abelian subgroup such that the quotient is finite. Okay, and one more thing, because now I really don't want to deal with this product case, is we call W gamma irreducible if gamma is connected, so the defining graph is connected. So it doesn't split in an obvious way as a direct product. Okay, and what one can show is that W gamma is irreducible and affine if and only if gamma is one of these graphs. And how does one do this? Well, this again works with this representation. But now one can show that W gamma is affine if and only if this matrix A is positive semi-definite and not positive definite. So now, essentially, these affine Coxeter groups come from taking a finite one and essentially adding one vertex, which in itself is, I mean, to me, this is just amazing. So you take something that's finite, which sort of corresponds to, well, I mean, they are called spherical Coxeter groups because they have something to do with nice actions on spheres. And now you add one more generator in a nice way, and now, boom, you have a very nice action on Euclidean plane, or Euclidean space, sorry. Okay, and sort of this is the final part that I want to tell you about, and this is the active research. And what is usually a good question, or well, one of the main questions that's asked for Coxeter groups is, okay, let's say my Coxeter group W gamma is supposed to have some group theoretic property P. How does this relate to combinatorial properties of my graph gamma? And now I'm going to give you some list of some properties and how they connect to properties of gamma. And this is a theorem, and this is not a conclusive theorem. Of course, there are many more properties that can be, in a sense, read off the defining graph of a Coxeter group. Okay, so the first one is finiteness, right? I gave you the classification. Affine, this is the same. You just look at the classification, and you, in a sense, have to potentially account for products. The next one is being Gromov hyperbolic. If you know what that is, great. If you don't, it doesn't really matter. But the condition is that there's no obvious z-square in the graph. And this can be phrased in terms of the graph gamma. Essentially, what you don't want is you don't want to have a direct product of two infinite Coxeter groups. And you don't want gamma to contain a big affine subdiagram, because if you remember, these affine Coxeter groups act nicely on Euclidean space. Well, if this Euclidean space is very big, then you always get a copy of z square, and then you can't be Gromov hyperbolic. So essentially, you don't want an affine subdiagram which has three or more vertices. The Coxeter group is virtually free. Well, how do you tell this from the graph? Well, you need every complete subgraph to define a Coxeter group. So complete means all vertices are connected by edges, and no induced subgraph is a circuit of three or more vertices. Sorry, of more than three vertices. You can have three, but not four. Okay, so this can be checked, right? If you're given a Coxeter graph and you take some time, then you can check this. Unless it's like 7 billion vertices big, then you ask your favorite computer to check this for you. And the final property I want to mention is the abelianization. So the abelianization of a Coxeter group W gamma is always isomorphic to a direct product of copies of Z mod 2Z. And it's very easy to check what this exponent is. You have to look at the number of connected components of the subgraph gamma odd. And gamma odd is just the subgraph you get by removing all edges with label, well, an even number or infinity. And then you look at the connected components and then you count them and then you get the exponent. And that's all I wanted to tell you about Coxeter groups. Sorry for going 2 minutes over time. I hope I could motivate you that these are very interesting groups. At least they are very dear to my heart and I really love doing research on them. And these are the books that I would refer you to if you want to learn more, or you can always ask me if you have any questions.